is to look on the Lagrange multipliers and to understand how the Lagrange multipliers help us solve uh, optimization problems with constraints. So we want to have a function with constraints, and we want to find the maximum or minimum, namely the optimization points of the function constrained by some constraints. So we have a function, this is our function, we have variables of the function x1 to xn, and we have constraints that we need to formulate in the formula that the constraints equals 0. For each constraint we have. The Lagrange multiplier we are building is built from the function and from the constraints. So here's the Lagrange multiplier. Those are the variables from the function, and lambda 1 to lambda n m is lambda for each constraint. So this is the function, and I add to it each constraint when it equals to 0 times the lambda of its constraint. Namely, I multiply each constraint with its Lagrange multiplier with its lambda that I just added here, and the lambda is unknown. We will find it, and using this we will find the maximum or minimum value, the optimization values of the function f constrained by those constraint functions. So this is the Lagrange multiplier we built from the function and the constraints. Now we are going to take the derivative of the Lagrange multiplier uh, for each of the values, for each of the parameters, for each of the variables of the function f, and for each of the multipliers, the Lagrange multiplier lambda 1 until lambda n. Now, taking the derivative of the Lagrange multiplier uh, in regard to each of the Lagrange multiplier will just give me the constraint when it equals to 0. This is why we should take every constraint and change it such that it will be something equals 0. And we need to change every constraint to be in this formula. So we're taking the derivative of the Lagrangian we built with respect to each variable of the x, which are the variables of the function, and with respect to the Lagrange multiplier, each Lagrange multiplier, which will be just a constraint. So we already know what it is. So let's see an example. So here it is. We have a function. It is depend on two variables, x and y, and the function equals to x squared plus y squared. The function is subject to the constraint g of x and y equals x plus y minus 1 and equals 0. If it was like x plus 1, y equals 1, I should have moved the 1 to the other side, so the constraint will be something equals 0. Okay, now I build a Lagrangian. I take the function I have, which I want to find the maximum or minimum, the optimization point, and here it is, and I put it here. Plus, I take for each constraint I have just one here. I add to it its Lagrange multiplier. This is lambda. I have only one lambda 1 because I only have one constraint, and I multiply it by the constraint which equals 0, which equals 0. So I need to organize it so it will equal 0 as it is now. So this is the Lagrangian. Now we'll take the Lagrangian derivative with respect to x, the Lagrangian derivative with respect to y, and the Lagrange derivative with respect to lambda. Each one of them will be equal 0. It is also called first order necessary conditions. So taking it with respect to x, I get this. When it equals 0, I can isolate lambda and get this. With respect to y, I get this. Yes, with respect to y, this is gone. This is becoming 2y, and this becomes lambda. So lambda here is minus 2y. And with respect to lambda, it's just this equals 0, which is exactly the constraint when we build it as equals 0. So here are from the first derivative, those are the equations, and I want to solve this system of, this is linear equations. So I solve this, and this, so I plug in instead of, I can say that lambda equals minus 2x, lambda is equals minus 2y, so I say that minus 2x equals minus 2y, so x equals y, so I can plug it into the constraint, and I can get that, let's say that y equal x, so x plus x minus 1 equals 0, so 2x minus 1 equals 0, so x equals half, and because x equals y, so y also equals half. So I got a solution of the function subject to the constraint. So now what it is it a maximum or minimum? So I need to plug it in, plug it in the function, and I get the value half. Now of course there are this is a convex function, so it has only one minimum, so it must be what we found, it's a minimum. Because if you take any another values, let's say that the constraint is true for it, let's say, I don't know, 3/4 plus, I don't know, uh, 3/4 plus 1 divided by 4, so it will be more than half. So the point we found is lower than an arbitrary value. So if it is an optimization problem, this is a convex function, so it must be a minimum. So we got a minimum value. So here you saw how I used the Lagrange multiplier, how I used the problem with constraints to find optimization problem, formulated the constraint in this form, built the Lagrange multiplier from the function and the constraints with the Lagrange multiplier, multiplying the constraints, taking the derivatives, calculating the linear equation we got from this, or the equations. I don't know if it was it doesn't have to be linear equations. So calculating the equations we got from this, and get a solution, which is the optimization problem of the problem subject to the constraint. So this is how we use and build Lagrange multiplier. Thank you very much. If there are any correction or mistakes, please correct me. This was about Lagrange multipliers in optimization problems, and that's it.